In this next lesson for homework packet 4.1, we're going to continue to look at domain and range. But instead of looking at it in the context of a graph, we're going to start with an equation. And from an equation of a specific type of equation family, can we determine the domain and range of the function? We'll start with a function family that we know, and that's linear. We know that the slope-intercept form of a linear is y equals mx plus b. That's what I've got right here, y equals 3/2 x minus 4. The question is, just by looking at a linear equation, can I determine the domain and range? Now remember, domain is all of the inputs, all of the x's. In other words, are there any x values that I could put in there that would produce wrong results or undefined results or results that don't exist? And then range is, what are the values that I can reasonably expect to get out for the y's when I plug in x's? Now, linear equations are fairly straightforward. Let's remember really quick how to graph something like this. If we remember, we start with the y-intercept, which is -4. So on my graph over here, I'm going to go down to -4. And then I'm going to use my slope of 3/2. That's up 1, 2, 3, over to the right 1, 2. Up 1, 2, 3, over to the right 1, 2. And there's the line, there's the graph of my equation, y equals 3/2 x minus 4. The question is, what is the domain and range? What you'll notice is, for the vast amount of linear equations, that the domain and range is all real numbers. Let's look at domain. What is the domain? We know that the domain is our x values. And in this case, the domain equals all real numbers. Why? Because when I look horizontally, left and right, my graph goes down and to the left forever, up and to the right forever. In other words, it goes to the right and to the left forever and ever. There's no boundary that my graph will get to and say that it can't go anymore. It'll cross that boundary and keep going forever and ever in both the left and the right direction. So we say then that our domain is x equals all real numbers. We can use that same exact argument for the range. We know that our graph goes up forever and down forever. Therefore, there's no boundary up here or down here that I could draw that my graph will never get to. So my range is y equals all real numbers. In fact, for the vast majority of linear equations, the domain and range are y equals all real numbers for the range and x equals all real numbers for the domain. We're going to look at three other function family types. One that you've graphed before in Algebra 1, but then two that you haven't yet graphed. We're going to take a look at one of those right now. We're going to take a look at the radical equation family. Remember that a radical equation is an equation that has a radical or a root in it. In this case, a square root. You'll notice both of our example equations down here have a square root in it. And the key is that the x value is underneath the square root. That makes these radical equations. The question is, what is the domain and range of a radical function? Well, we need to know something about what a radical function or a radical equation looks like. Over here, I've got what the basic form of a radical function looks like. We know linear equations give us straight lines. We know that quadratic equations give us parabolas. Well, what does a radical equation give us? A radical equation kind of gives us a half of a parabola tipped over on its side. If I were to reflect it over here, you could see the full parabola, but it's only half of a parabola. And instead of opening up or opening down, it's half a parabola that, if we were to have the other half, would open to the right. Now, a radical equation okay, always opens to the right. Okay? We're always going to have this starting point right here, and it's either going to go up and to the right, or it's going to have some starting point and go down and to the right. Now, in order to determine the domain and range, we need to know where that starting point is, and we also need to know whether it opens up and to the right or down and to the right. And here's how we determine that. This right here is the standard form of a radical equation. What's nice is that starting point is given to us in the form of the equation. You notice that this says right here the starting point is the point hk. Here's h, here's k. H is the value next to the x underneath the square root. K is the value outside the square root. So when I look at this example here, what is my hk? Well, my hk is actually -2, -4. H coming from underneath the radical, k coming from outside the radical. My k is -4. Now some of you might be looking at that and saying, wait a second, isn't the h a +2? But take a look at what's under here. The standard form of a radical is not a times the square root of x plus h, it's x minus h. So in other words, what do I have to put in for h for this to end up being a +2? It actually has to be a -2 right here to get the negative and negative to cancel out and give me the +2 that I have in my example down here. So the key way to think about it is underneath the square root, always think opposite. So instead of 2, -2. So I know my starting point is at -2, -4. The next question is, does it open from here up and to the right or down and to the right? Because that affects what my domain and range are. And that's determined by this value a in front of the equation. If a is greater than 0, it goes up. If a is less than 0, it goes down. So if a is positive, it goes up. So in our example here, a, the value of 3, is positive, so I know it goes up from here. Okay, now I don't know if it goes really flat or way high up. It really doesn't matter, because if from my starting point here it goes up and out, the question is, what's my domain? My domain is x what? I look at my starting point and I notice that my graph only goes to the right of this starting point. It never goes to the left. So I would say then that my domain is x is greater than or equal to -2, because it never goes below this boundary of -2. My graph doesn't exist over here. It starts here and only goes to the right. We can use that same logic for range. Range is y. Well, in this case, in the y direction from my starting point, it only goes up. It never goes down from the starting point. So I know then that my range is y is greater than or equal to that value of -4. That's my boundary right here. My graph is always greater than or equal to -4. It never goes down here. It only exists above -4. So my range is y is greater than -4. Great. Let's look at that one more time over here in this example. Okay. So we want to start with finding our starting point, hk. I know it's the value underneath and the value outside, hk. But remember, underneath you have to think opposite. So you have to think, instead of -3, you have to think +3. So hk for us is not -3,4, it's +3,4. So if I go over to +3, +4, there's my starting point. Now the question is, again, does it go up and out from there or down and out from there? I look at my front value here, the a value, and I see that it's negative. Therefore, it opens down. So from here it goes down and to the right. So what then is the domain and the range of this function? Well, the domain is that x has to be greater than or equal to, looks like the boundary there is a 3. And my range is y has to be, careful here, because in this case it's not that my graph is always above a certain value. In this case, it's that my graph is always below a certain value. It's below this value of 4. So my range is y is less than or equal to 4. It's always less than or equal to 4. So there's domain and range in the context of a radical equation. The next function family that we want to take a look at is exponential functions. Exponential functions are functions of this form right here. We've seen these already. Y equals a times b to the x plus k. In other words, we can just add some value to the end. Okay. What makes an exponential function an exponential function? The value or the variable x is an exponent. So rather than it being something times x, it's something to the power of x. That makes it exponential. Okay. Now, there's one key feature to an exponential function that allows us to determine the domain and range. Okay. So I've got several examples down here. I've got y equals 14 times 0.6 to the power of x minus 3. So again, notice it's to the power of x, therefore it's exponential. Over here, same thing. It's 2 times 1.3 to the power of x. So both of these are exponential equations. Okay, so looking at that then, what we have now is we have two scenarios in which we need to find what's called the horizontal asymptote. So what does an exponential function look like when you actually graph it? Okay? An exponential function always has this thing called a horizontal asymptote. It's a boundary. So let's say this is x and y. It's some boundary. And that boundary defines the lowest point in all the examples that we're going to look at, the lowest point that our graph can go. Okay? In fact, it represents even a little bit more than that. It's that our graph is always above that specific line. Okay? So it'll maybe look something like this. It levels off along that line and then increases on the other side, or it starts high, comes low, and then levels off at this line. But in both cases, notice that it never goes below this dotted line that I've drawn here. This dotted line right here is the horizontal asymptote. Okay? So where is the horizontal asymptote for a given equation? Simply put, it's the value of k. So in this first example right here, what's my value of k? My value of k is a -3. And notice it says the horizontal asymptote is at y equals k. So y equals -3. I'm going to go down here and I'm going to draw a line at y equals -3. That's the boundary. I know that my graph doesn't go below that line. Okay. What's my boundary over in this example here? Well, what's my value of k? It's that last constant value. It's a 4. So I know that my boundary is now right here. Second thing that you don't necessarily need to know to find domain and range, but it'll serve us in the future when we are a little more detailed in graphing these, is to be able to know whether it looks like this here, where it starts high and then levels off, or it starts leveled off and then ends up high. We call this one growth because it starts low and goes high. We call this one decay because it starts high and goes low. Okay, so which one is which? You'll notice right here it has everything to do with a base multiplier. That is the value of b, the value that the variable x is connected to. Okay. If b is greater than 1, it is decay. In other words, it starts high. Oh, I'm sorry, it's growth. It's growth if b is greater than 1. which means it starts leveled off and goes high. Now, if b is between 0 and 1, notice b will never be negative. It's always going to be between 0 and 1 or greater than 1. Then it gives us decay. That means it starts high and goes low. So in this first one, I notice my base multiplier is a 0.6. That's between 0 and 1. Therefore, it's decay. I know it starts high and then levels off. In the second case over here, this is a 1.3. That's greater than 1. Therefore, it's growth. So it starts leveled off and goes high. Now, the important thing to remember is this. In both cases, an exponential equation always goes forever and ever in both directions horizontally. It goes forever to the right and forever to the left. All exponential equations do that. So because it goes forever and ever in both directions horizontally, we know that our domain is always x equals all real numbers, because there's no boundary, there's no value that it cannot at some point get to. However, our range is what we have to pay attention to when it comes to exponential equations. So in this case, our range is where we look vertically. It's our y-axis. It's the y variable that we're looking at. And what I notice is that my graph is always above this horizontal asymptote. And I know my horizontal asymptote is at -3. So I'm going to write my range as y is greater than -3. So this is implying two things. First off, my graph never exists below -3. It always exists above -3. Furthermore, this implies that it never actually touches this horizontal line. It's always greater than -3. It never actually gets to -3. It's an important concept. Okay. Over here, what's my range? I notice that it's always above this value of 4. So my range is y is greater than 4. So again, with exponential functions, any function of this form right here where the x variable is the exponent, your domain is always all real numbers, and your range is determined by the location of the horizontal asymptote. Last type of function that we want to take a look at that you've seen before already in Algebra 2 is the quadratic function. That's the f of x equals ax squared plus bx plus c. We've already worked with these functions. And from Algebra 2, you already know that it gives you the graph of a parabola. Okay? There's this point right here that you know is called the vertex. And from that point, the graph either opens up or, in some cases, that the graph opens down. So the question then, in order to define or to find the domain and the range of this function, we need to know where that vertex is and whether or not the graph opens up or down. Those two pieces of information will allow us to state the domain and range. So let's first start by finding the vertex. We've got the x-coordinate and the y-coordinate of this vertex. Every vertex is on a specific location on a coordinate plane, and every location on a coordinate plane is defined by an x and a y coordinate. Now, you found these the vertex in this way in Algebra 1, but it's been a while, so here's the reminder. We have a formula here to find the x-coordinate of a vertex of a parabola. It's -b over 2a. Where do the a and b come from? It comes from the a, b, and then c right here. So in this first case, my value of a is -3. In this example here, my value of b is 12, and my value of c is -8. So how do I find the x-coordinate of my vertex? -b over 2a. So -b is 12, all over 2 times a is -3. So I believe that gives me a -12 over -6. 12 over 6 is 2, and a negative over negative gives me a positive. So I know that the x-coordinate of my vertex is the value x equals 2. But what then is the y-coordinate of my vertex? All you have to do is take the x-coordinate that you just solved for and plug it back into the equation. So let's take this 2 and plug it into our example right here. That's going to give me negative 3 times 2 squared plus 12 times 2 minus 8. All I'm going to do is plug that in exactly as I see it with those parentheses in my calculator. Negative 3 parenthesis 2 close parenthesis squared plus 12 times 2 minus 8. And I'm getting the value of 4. So what this is telling me is this, that my vertex is at the coordinate point 2, 4. X is 2, y is 4. So 1, 2, 1, 2, 3, 4. The coordinate point 2, 4, that's the location of my vertex, like the vertex of this parabola over here. Now the second question to answer is, from this point, does it open up or does it open down? And that's answered simply by looking at the value of a. If a is greater than 0, in other words, it's positive, it opens up. If a is less than 0, meaning a is negative, it opens down. In our case, a is negative 3. That's less than 0, so we know that the parabola from my vertex point is going to open down. It could be skinnier, it could be wider than the way I've drawn it, I don't know, but at this point I don't care because all I'm determining is domain and range. Now the key is to remember this, with domain of a quadratic, because my graph always goes out forever and ever in both directions. Yes, it's going down on each side, but it's going down and out left and right on both sides. I know that the domain of a quadratic is always going to be x equals all real numbers, because there's no boundary that I can draw on either side here that would that my graph wouldn't at some point cross over. There's no boundary whatsoever. So my domain is all real numbers. However, my range, from my vertex here, I never go above that point. I'm always going down from this point. So my range is going to be y is less than or equal to that point. And what's the y value of that point? It's a 4. So my range is y is less than or equal to 4. I'm always less than or equal to that value of 4. I never go above that value. So there's domain and range of a quadratic. We're actually going to look at a quadratic one more time, but we're going to look at it in the form of a quadratic that you may not be as used to. So let's look at this other form. It's called vertex form of a quadratic. You'll see here it's f of x equals a times x minus h squared plus k. It's still a quadratic, so it still has a vertex, and it still either opens up or down. And here's our example, y equals 3 times x minus 4 squared plus 2. How do I know it's still a quadratic? Because my x value is being squared. We know something's a quadratic when the x value is being squared. Now what's nice is finding the vertex is really easy in vertex form. It's simply the point hk. It's the same as the radical that you'd already taken a look at, except instead of this being under a radical, this is being squared. But it's still the point hk, and we still have to be careful with that h, and we have to think opposite. It's inside the parenthesis that's being squared. So in our example right here, here's the h, here's the k. But instead of negative 4 for h, what is actually h? It's a positive 4. You have to think opposite. K, the outside number, is 2. So just like that, I already know my vertex is at the point 1, 2, 3, 4, 1, 2. So 4, 2 is the value of my vertex. Okay, so I know from here that I either open up or I open down. question is, which one? And I determine that the same exact way as the other form by looking at the value of a, the value out front. If it's positive, it opens up. If it's negative, it opens down. In this case, it's a 3. That's positive, which means it opens up. So I've got a quadratic that opens up here. The question now is, what's my domain? Well, we already know that because it goes out forever and ever in both directions, the domain is x equals all real numbers. It's the range that's in question. The range is what? Well, in this case, I've got this boundary right here at my vertex, and my graph is always above that boundary. It never goes below. So I'm going to say that my range is y is greater than or equal to that boundary of 2. I never go below 2. I'm always at 2 or above it because I always open up from my vertex for this specific example. So there's domain and range in the context of what we call vertex form of a quadratic. How do you find the vertex? It's really fast. It's the value hk. But always remember that h, you have to think opposite.